My name is Phil Ledent with the Masonry Institute of Michigan, and today we're going to look at how to evaluate an unreinforced masonry wall based on our TMS 402, the 2016 edition. And so to do that, we'll look at a wall. And I just drew a wall up this morning. So let's say we have a 16-foot wall height from finished floor elevation to the top of our wall. And let's say this is an interior partition wall, and we'll use type S masonry cement mortar. So let me write that here. So we'll have type S, and that's going to be a masonry cement mortar. And so we'll use that type of mortar to determine what our capacity is of this wall in terms of flexure. And so just looking at this detail real quick, I drew it up so we want to be pinned at the top and the bottom of the wall. So at the bottom of the wall, I have a rebar dowel going into a thickened slab. And so a critical part of designing walls is for construction. And so if this is a partition wall, there's a chance maybe we're going to have to build this partition wall before the building is enclosed. So we don't want that partition wall blowing over during construction from any wind gusts. And so there are ways to design it as what's called internally braced, and we'll record a future video on that topic. But for a wall to be considered internally braced, typically we are designing it based on our standard practice, which is a document developed by the MCAA. And so we'll be resisting 40-mile-an-hour wind loads. And so we have some dowels here. So during construction, we can leave this wall cantilevered from our thickened slab without the roof on it and make sure that we are safe from it blowing over during construction. Once it is built, we will have some continuous 12 gauge angles at the top of our wall that will connect to our light gauge roof deck to pin at the top of our wall. I did show a bond beam here. However, if we are designing unreinforced masonry, we disregard the effect of any reinforcement in the wall. I just showed that in case we wanted to anchor in here. We know it's fully grouted. And if this is a firewall, we would want to have some type of a condition at the top of the wall with mineral wool or ceramic fiber felt or something that gets us an approved detail to make sure that we maintain our fire rating for this wall. So again, we have a 16-foot tall wall height. We know we have type S masonry cement mortar. This is 8-inch CMU. And because we're in Michigan, a lot on the east side of our state, we use normal weight units. So we'll say our density of these units is 135 pounds per cubic foot. And so the first part of solving this, we need to know what our design parameters are. So we recorded an earlier video on how to calculate our net section properties, but in the interest of time, we'll go to NCMA Tech Note 14-01B, which gives us our section properties. So if we go down to our 8-inch wall table here, and we'll copy this into our example. If we have an 8-inch wall and we are ungrouted, we can pull all of our parameters directly from this table. And so here, again, we have hollow, no grout in it because we're disregarding that grout. At the bottom of our wall, we have mortar face shell bedding, and we talked about that in a previous video. And so our net section properties that we'll be using for design are given here. So we have a net area of 30.0 inches squared per foot. We have a net moment of inertia, I net, of 308.7 inches to the fourth per foot. And we have a net section modulus of 81.0 inches cubed per foot. So now we have all of our net section properties. We need to know the weight of our wall, which we can get directly from another tech note. And so if we go to Tech 14-13B, which is published by the National Concrete Masonry Association, this gives us all of our concrete masonry wall weights. So if we scroll down here and go to the table for 8-inch CMU, and I'll just copy this in our example. But if we have hollow units, no grout, and face shell bedding, and we have a density of 135 pounds per cubic foot, we get a wall self-weight of 39 PSF. So let me copy this table in here just so we can refer to it later. And so again, with 135 PCF density, our wall self-weight is 39 PSF, which wall self-weight is very, very critical when we are designing unreinforced masonry. So wall weight will have 39 PSF. The other thing we need to know comes out of our TMS 402. So if I open that up, we have a table in chapter 9, which is strength design, which is what we'll be focused on today, which gives us our modulus of rupture values. And so I'll take a snip of this to copy into our whiteboard. And this will give us our flexural tension capacity for our walls. So let me paste this down here. And so if we have an ungrouted hollow unit wall, which is what we have, and we need to know the direction of our flexural tensile stress, whether we're normal or parallel to our bed joints. We know we have an internal pressure, which we'll talk about in a second, blowing on our wall out of our IBC. So we have this pressure, this uniform load blowing on our wall. That's going to create stress in our wall, where we're going to have compression on one side and tension on the other. And the direction of that stress is going to be, as you see here, normal or perpendicular to our bed joints. So we'll be looking normal to our bed joints, and we'll be looking at hollow units ungrouted. And in the problem, we said we had type S masonry cement mortar. So if we go here, masonry cement mortar type S, we get a value of 51 PSI for our modulus of rupture. And so F sub R is going to be 51 PSI. Now, the last thing we'll need to know is our phi factor for our design. So if we go to chapter 9, which again is our strength design chapter, all of our phi factors are early on our strength reduction factors. So combinations of flexure and axial load in unreinforced masonry, our phi factor is 0.60 for unreinforced masonry subject to flexure, axial load, or combinations thereof. And so our phi in this case is going to be equal to 0.60 for this problem. All right, so now we have all of the information about our wall. And so now we need to know what that uniform load is that gets applied to our wall. And so for our case, that comes out of our International Building Code, specifically out of chapter 16, which is structural design, and our IBC is available free online. This is our 2018 version. And so if we scroll down here, we have interior walls and partitions in section 1607.15, and it says interior walls and partitions that exceed 6 feet in height, including their finished materials, shall have adequate strength and stiffness to resist the loads to which they are subjected, but not less than a horizontal load of 5 PSF. And so it's not clear in ASCE 7 or in the IBC what type of load that is. And so normally I assume a load factor of 1.6, which is our load factor for live loads. And so that way we're a little bit conservative in our design with our strength level loading conditions. So if we are taking this as a live load, usually I take 0.9 dead, which would be our minimum dead load resisting this. And so we'll add plus 1.6. And I'll just call this P for our case, but we'll have a partition load, which in our case is 5 PSF. All right, so we have all of our loads, we have all of our design information. So now we just need to check our stresses in our wall. So to check our stresses, we'll have minus our axial load, P sub U, divided by our net area is going to give us our compressive stress, which is a uniform load acting down on our wall. And then we'll add our design moment, M sub U, divided by our net section modulus. And that will be our flexural stress on our wall. So on one side, it will add to our compressive stress. On the other side, it will subtract from our compressive stress. And we need to make sure this is less than or equal to our strength reduction factor phi times F sub R modulus of rupture. And so we can solve for all these variables. So P sub U, our axial stress, and because this is a uniform load acting on our wall, we know that our critical point for that wall is going to be mid-height of our wall, where we will have the maximum moment occurring. And so we want to take our axial load at mid-height of our wall. So we would have 0.9, our load factor for dead load, times our wall weight, 39 PSF, times our wall height, 16 foot, and we'll divide that by 2 to get our weight at mid-height of our wall. And so this will come out equal to 280.8 pounds per foot. And again, with most of our wall designs, we are designing them based on a per foot basis of our wall. So that's what all of our properties are in. And that's what we're solving for here in terms of our load. So we have piece of view, a net, our net area, we know from NCMA's table or from our previous video, we know how to calculate that, 30 inches squared per foot. Our moments, sub U, we're going to take our load factor of 1.6, again for live load, times our 5 PSF, our interior wall and partition load out of our IBC, times our wall height, 16 foot squared, and we'll divide that by 8. And this is just the formula for calculating maximum moment for a uniformly distributed load, WL squared divided by 8, which hopefully everyone is familiar with. And so plugging that in, we get a moment of 256 foot-pounds. And again, that's measured per foot of our wall. Last thing was our net section modulus, which we looked up in our NCMA table, is 81.0 inches cubed per foot. All right, so we have everything we need to plug in and check our stresses. So we'll have minus our axial load, 280.8 pounds per foot, divided by our net area, 30.0 inches squared per foot. And then we'll add our flexural stress, so 256 foot-pounds per foot, and we want to convert that into inches, so we'll multiply that by 12 inches in a foot to get that into inch pounds, and then we will divide that by our net section modulus of 81.0 inches cubed per foot. And we multiplied that by 12 so that we can cancel our inches in the denominator here. So we come out with a PSI per foot of wall. And so adding those two together, we get a flexural tension stress of 28.56 PSI. All right, so now we just need to compare that to our resistance side of our equation. And so we have phi times our modulus of rupture, which we know our phi for unreinforced masonry is 0.60. Our modulus of rupture for type S masonry cement mortar normal to our bed joints was 51 PSI. 0.6 times 51 gets us to 30.6 PSI. So that's our allowable flexural tension stress, 30.6 PSI, and indeed that is greater than our applied tension stress of 25.56 PSI. And if we wanted, we should check the compression side as well, but with a 5 PSF interior load, we know by inspection that we're not going to exceed our allowable compressive stress on the other side of the wall, because like I mentioned with our flexural stress, it's going to subtract from our axial stress on one side, add to it on the other, so we should really check the compression side, but by inspection, we don't need to in this case. And so we have shown that if we have a 16-foot tall interior partition wall, and we are exposed to that 5 PSF interior wall and partition load out of our IBC, if we use type S masonry cement mortar, we have adequate strength to resist that load. And I did develop some tables, which we also have posted on our website, which give us the maximum heights that we can go based on different mortar types. And so if you're curious about that, you can certainly go on our website and get those. Hopefully this made sense. If anyone has any questions on calculating capacities of unreinforced masonry, please let me know. Thank you for listening.